Hi, I'm Carl. In this video, we're going to have a look at questions 66 to 68 in section 3 of the purple booklet. This is about water pressure, and we were given quite a lot of information, which I've summarized into some of the equations and what all the letters stand for. It can be a little confusing because there's so many letters that look the same in this, but I'll talk you through what each of the questions mean. 66 says a horizontal tube with a diameter of 2d branches into two horizontal tubes, each with diameter d. The branch of liquid flow in the first tube is v. What is the speed of liquid flow in each smaller tube? So this sort of thing, I think it's easiest just to sort of draw a diagram. So we've got a larger tube, which is horizontal, like this, and it's got a diameter of 2d, which I'll draw in here. It branches off into two other horizontal tubes, and each of these have a diameter of d. Water is flowing through at a rate of v. We want to see what the water flow here is. So we've been given a number of equations, and the one that's most useful here is going to be the first one, which is saying that the cross-sectional area times the volume, or the flow rate, has to be constant. So in this tube, I'm just going to draw a line here, and we divide it into two parts. Before it branches in, there is going to be a particular cross-sectional area with diameter of 2d. Then whenever it splits off, each branch has a diameter of d, which means the cross-sectional area goes from being 2 to 1. There's a 2 to 1 ratio of the cross-sectional areas because the diameter halves, so does the cross-sectional area. So if the cross-sectional area times the volume equals a constant, or times the flow rate equals a constant, if we half this, in order to keep C the same, we need to double the flow rate. If you half one, you need to double the other to keep the product the same. Therefore, the speed of liquid flow in each smaller tube has to be twice the number of the original. So therefore, the answer for this one is going to be C. And that's just because you're halving the amount of area through which the fluid can flow. So questions 67 and 68 talk about possible designs for a new dam, and I've sort of tried to copy them out here. 67 says, for which design will the water pressure at the base of the dam be the greatest? Well, we were given again a couple of equations, and the one that tells us a little bit about how depth affects pressure is number 4 here. And we can see that the pressure is proportional to the depth below the surface. Now, this one can be a little bit confusing because the 3 different dams in the diagrams shown in the paper sort of look like the lowest point could be a little lower for some than for others. The base of the dam, therefore, will be lower and would have more pressure for, say, 3 than for 2, because it just looks in the diagram that it's going to be a little deeper. But looking closer, you can see that they're actually all the same depth, and if the depth is the same for all of them, the pressure has to be the same. The shape of the dam doesn't affect the pressure that the water is exerting on it at the very base. So that means the pressure has to be the same in all 3 designs because the depth of the dam is going to be the same in all 3 designs. So that means that the answer for number 67 has to be D. And that the pressure down at the bottom here is going to be the same because the bottom point is always going to be the same between the 2 or the 3 designs. Okay, so for 68 then, it says, for which design will the total force of the water on the dam be the least? So there's a couple of different ways of thinking about it, but I think the most intuitive way is looking at the surface area. The surface area of the dam is the amount of material that's going to be exposed to the total force of the water. And so if you lower the surface area, you're going to be lowering the total force. So we're going to look at which design has the smallest surface area exposed to the water, and that's the one that will have the least amount of total force from the water. So it could be a little bit confusing from the way it's shown here. I don't think the diagrams are overly helpful, but if you look at just the portion of the dam that's going to be exposed to the water, you're really just going to look for the shortest line. And of course, they're all going to have the same length, same height, sorry. So which line is going to be the shortest in distance? Well, if the depth it has to overcome, which is going to be this, what I've drawn in the red arrow, is going to be the same for all of them, then you know maybe from triangles that a vertical line will be the shortest path from the top of the water down to the bottom. And if it's at a curve, it'll be an even longer one. And that's true for this one and this one. The sloping of the dam doesn't necessarily have an effect on the surface area that the water is going to be pushing against. Although, of course, there is going to be different pressures at different depths. So the reason why people might want to pick this one is because the pressure is going to be the least up here, and this is where it's thinnest, and then the dam should be strongest here. And then down here, because it's thicker, where there's more pressure, it might be better. But that's not what the question was asking. It says, which design will the total force of the water over the entire depth on the dam be the least? And of course, then the answer for this one is going to be A, because it is the least surface area. This is one of those questions where they give you much more information than you need, and it seems a little confusing, but actually break it down. You really only need two of the more simple equations. So I hope that helped.